Yes,
in regular mode?
yes, we are.
Perfect. So I'd like to first acknowledge my colleagues, John Plumley, Lakun Sui, and Tom Peng in the development of reversible electrochemical mirror/windows using cationic conducting membranes. So the terrestrial application for this is really for smart windows. For those of you who have visited some of the newer buildings, for example, Ferris Hall, there are windows there which can actually change their ability to either reflect or to transmit light. And the inflow of light or the inflow of heat accounts for a very large factor in building energy utilization, and so therefore in CO2 emissions, because these buildings are cooled with electricity from fossil fuel. And so energy loss through conventional windows can account for about 30% of the heating and cooling energy losses. And the DOE has an extensive building technology office which has been studying this for a long time. And it was actually DOE funding which brought us the electrochromic window technology which exists today. And so very quickly, light shines on a window. This is an illustration of a double glazed window. The heat which is transmitted will warm up the room, which is occurring right now in my office. I just checked my office window temperature. It is 93 degrees and the room temperature is 78 degrees. So obviously there's a heat flux coming in. Visible light is also transmitted. This heat loss also by infrared radiation out of the window. And so there's been a lot of work done at improving window technology over the years. The standard one is clear glass with a low emission coating, argon gas to reduce the thermal conductivity between the two glass panes. If you visit Ferris Hall, for example, you'll see sage glass in action. I have it actually in my office in Ferris Hall. And here's an example from their site of sage glass, which is an electrochromic technology which can electrically change the transmission of light. And this is pretty much the range which you get. You go from a light blue to a darker blue here. Now this is the lower illustration is their minimum light transmission. So you can still see there's a fair amount of light being transmitted, but it is doing a good job at blocking. It's certainly better than conventional window technology. What would be ideal would be to have an electrically reversible mirror technology where you go between being a mirror and a window. And there are coatings, and we can see these applied, for example, on the right-hand side here to a partially silvered coating being applied to, it's probably an aluminized coating being applied to a window. Now this can reduce your heat, load, but for example, if you actually in the wintertime want the solar heat, there's nothing you can do about this except for to remove the film or remove the window. And these do not completely block out the sunlight. So a smart window technology can maximize interior sunlight for solar heat when you want it, and light gains during cold periods. The mirror technology can reduce your heating loads. Smart mirror technology also has another benefit with privacy, that you can completely block out the ability for light to go in and out, so people can't see what's going on inside. And if it's a metallic film, it can provide reversible EMF shielding. You can completely block out the ability to transmit information back and forth via wireless communications. And this can be very desirable for privacy applications. And so what you'd like to have is the ability to go between almost complete reflection of incoming light in mirror mode and complete transmission in window mode, substantially higher than existing electrochromic smart windows, which exist today. So what initially funded this program was heat control in space vehicles. And space vehicles have a huge problem in that when they're in the presence of sunlight, the temperatures can range over 200 degrees between being on the dark side of the Earth and being on the bright side. And so the Air Force Research Laboratory has invested quite a bit of work at being able to make smart windows to control the emissivity and the reflectivity of windows to control heat. And this was the funding source and really the driver in our system. So a little bit of background. We've produced reversible electrochemical mirrors with liquid electrolytes. We're not the inventors of this technology, but we have made some very substantial improvements to this technology, which can make this technology last for thousands of cycles. And the way this works is that in the reflective state, what you have is you have a thin film of indium tin oxide, which is transparent, with a small quantity of platinum, literally just a few nanometers of that. And what we do is we electrodeposit silver onto this transparent window, giving a mirror. And silver has some of the best reflectivity properties there is of any metal when it comes to reflecting the entire solar spectrum, visible and infrared solar spectrum. When we want it to go transparent, we strip this off and we convert the silver metal back into a molecular form, or we plate it in a non-visible part of the window. And this is showing a device where it's showing reflection. This is showing transmission. I'm going to switch my share here and go to a little video here. And let me change my share just to show you how this works. At the end of the day, it's nice to see a video or two, and also leads to credibility. Okay, so this is a small device. This is about a 4-centimeter device with our window technology, and we have an X written on the back side of this so that you can see that it is transparent. And I'm running it now. And this is in real time. This is changing in real time. And as you can see, the X is getting less and less visible. And you can start to see the camera, which is recording this because of the increase in the reflectivity of the mirror as we go from window technology, from being a window to being a mirror.
I think we're only seeing your PowerPoint still.
Okay, let me change this. Thank you.
There we go.
There we go. Okay, so scanning through in a 1-minute time frame, okay, you can see the X here, which is showing the transparent state. And as we move along in time, you can see the reflection now of the camera, which is taking the picture here. And now you can see the reverse cycle going back to the transparent state. And this entire time sequence is 1 minute in time, 1 minute and 13 seconds in time, in real time. So the devices work pretty quickly. I have another example here. Where you can see the change in the reflectivity of the device. This is a device which is using a grid rather than using converting the silver to molecular species. So we're going back and forth between plating it on the window and the grid. You can see back and forth the changes here. So these are just some very brief examples of what we have done with this technology. And we have come up with additives and improvements to this technology to make it last thousands of cycles. I'll skip that. That's just technical stuff. So for the, let me put this back into slideshow mode. And this is a diagram called Cyclic Voltammetry diagram, which basically follows the charge which is being used in order to convert the between a mirror and transparent. And these are multiple cycles. And essentially what this is indicating is the energy going into the converting silver into ions. In this case, what we're doing is we're making silver metal and bromine in solution. And then on the reverse cycle, we go back to silver ions and bromine ions in solution. So you can go to silver metal and bromine, which gives you the mirror, or you can go to silver ions and bromine ions, which is transparent in solution. And so this is an example of the change in the optical behavior. The reflectance is changing 82%, and the transmission is less than 1%. The rest are losses within the system. And we have run these devices for thousands of cycles. These are just superimposed some cycles from the first 3 cycles to cycle 2000 to 2003. We've run these even more. I think that they've gone over 5,000 cycles. So we're quite confident with this technology that we've gotten to the point where we can show good reversibility at room temperature with this technology. We can also change the color of the mirror by changing certain additives. This is just some of the additives which we have in here. And we can switch between silver to going to orange, yellow, green, blue, or dark red, depending on what the application is. So our mirror, so rather than going to transparent, we would go to a colored mirror. Now, liquid electrolytes have disadvantages. One of them is the sealing. They're leak prone. You got to worry about the toxicity of the electrolytes if you release them to the environment. Freezing may damage the windows, so you can use very low melting point, very low freezing point electrolytes, and the manufacturing becomes more difficult. You can't use conventional window glazing, window manufacturing technology. Now, if you go to solid polymer electrolytes, you can seal with there's no problem with leaking. If you use the right polymers, very low release to the environment, low toxicity, no freezing, no cold damage, and the manufacturing can be the same as conventional safety glass. And so this is an example of a precursor polymer film, which we use which we treat to make it the silver ion conductor, which we use. It's a very stable material, and it can be laminated between 2 sheets of glass, which are coated with indium tin oxide. So the technology is very similar to safety glass manufacturing. Now, the solid polymer electrolyte development is in its infancy compared to the liquid electrolyte development for a very simple reason. The Air Force is not interested in polymer-based devices because polymers degrade in radiation space environments. And there's some very nice, I can send it to people, ongoing experiments with NASA, which are basically trying to develop better polymers for space, but that's your first component, which degrades. So for the space applications, are happy with the liquid electrolytes. However, for terrestrial applications, we'd like to move away from those. And what we've done is we've developed transparent silver ion conducting polymers to replace the liquid electrolytes in the reversible mirror window technology. These silver polymers are derivatives of membrane now used in fuel cells. They're highly stable. There's very little environmental degradation and low toxicity of the parent material. And we've demonstrated proof of principle where we can go back and forth using a very similar procedure to what is done with the liquid electrolytes using silver salt electrolytes, and we've applied for provisional patent. This is just the change in the reflectance or transmittance. So there's over a 500% change with the polymer materials. However, the Air Force, they allowed us to play a little bit with the polymers, but they said, look, we're not interested in polymers. So we're seeking more developmental funds. We are speaking with a major window manufacturer now about working with the DOE Building Technologies Office for further development of this technology. But we think this shows a lot of promise. The window market is a huge market, and besides windows, there's earlier markets such as the eyeglass market, auto windscreens, applications such as those specialty markets. So just to conclude, we've developed reversible electrochemical mirror technologies with high cyclability over 3,000 cycles. The reversible silver electrode deposition shows very high promise for these variable mirror window devices. We believe that solid polymer electrolytes are the future because it can vastly improve the manufacturability of these devices. We have a provisional patent on solid polymer-based devices, which we are in the process of trying to convert to a full patent. We also have a lot of proprietary knowledge and development for liquid and gel electrolytes for reversible electrochemical window and mirror technologies. This work was primarily funded by the Air Force Research Laboratory. We're funded also through Space Dynamics Laboratory. We work with Faraday Technologies, a small company which is very good at electrode deposition. And we've had students from Princeton also assisting us with this technology. And Tench Technologies, Tench was the grandfather of the very, very, very first generation of these devices. But we've made significant improvements in that technology. Well, with that, I'll take any questions you may have.